Okay, so we're moving right along here in chapter 20. We're still focusing on the enzymes though. Hopefully we've covered a lot of ground and you're feeling more confident, and we're working our way up to those vitamins. Don't worry, we won't forget about them. Our particular focus for this relatively brief lecture, it will be factors affecting enzyme activity. So we've talked a little bit about what the enzymes do and how they are classified. Now let's talk about how their activity is affected. Okay, so looking first at temperature and enzyme activity, enzymes are most active at an optimum temperature, which is usually 37 degrees Celsius in humans. That's normal body temperature. That's what we hope to be at almost all the time. Again, fevers might send us up. Wintertime, certainly in the Northeast, sends things down slightly. If you're out too long, things can get dangerously low, but the enzymes in our body really need us to be right around that 37 degrees Celsius mark. They tend to show little activity at lower temperatures, and strangely, unlike what we learned back in General Organic Biochem 1, where we said increase in temperature increases the rates, if we go to higher temperature with the enzyme catalyzed reactions in our body, they actually lose activity at those high temperatures as denaturation of those enzymes, which are, as we said, overwhelmingly protein in nature. They do not work very well at higher temperatures. So low temperature is bad, high temperature is bad. Right around that 37 is good, and we see that on our graph. Reaction rate increases dramatically up to about 37 degrees Celsius, and then it decreases pretty dramatically starting at about 40, and then by 50, where those protein-based enzymes have all denatured, you get almost no activity, and that's why, of course, high fever gets to be a very dangerous situation, because as you go much over 40 degrees Celsius, as you see, activity drops off dramatically for these enzymes. Let's take a look now at pH and enzyme activities. Believe it or not, enzymes are most active at optimum pH, just like they're most active at optimal temperature. So the pH where proper tertiary structure of the protein is maintained. Here we're looking at the enzymes which contain our groups of amino acids with the proper charges at optimum temperature. So if we think back to the previous chapter where we talked about isoelectric points and things like that, that should make a lot of sense that we want to have these proper charges, and whereas human body temperature tends to be about 37 throughout the body, pH can change quite widely depending on if we're talking about the acidity of the stomach, the basicity of the intestines, the blood slightly basic, urine slightly acidic. So again, it depends on where we're talking for these enzymes in their particular optimal pH, but they do tend to lose activity in low or high pH as their tertiary structure gets disrupted. So if we're dealing with our typical blood-based protein enzyme, for instance, we see that the maximum enzyme activity happens around pH 7. The blood pH is slightly above 7, and we see slightly above 7 there for maximum enzyme activity. But if we go much lower than that ideal optimum pH, we start to have dramatic drop-off in activity, either lower or higher, because the side chains aren't going to be properly charged, and they aren't going to be able to fold correctly in anything that's much more acidic or less acidic than their optimum pH. Okay, so looking again in more detail, those optimum pH values tend to be around 7.4, which is again most of your blood and body fluids like lymph and things that are again in that controlled, slightly basic, just above 7 environment. However, certain organs have enzymes that operate at lower or higher optimum pH values depending on the jobs they do. So if we look here at table 20.5, pepsin, which is located in the stomach, its substrate is peptide bonds. It starts to break those polypeptides, those proteins. It catalyzes the hydrolysis of those amide linkages, and therefore it likes to do that activity at a very low pH. The pH of the stomach ideally is between 1.5 and 2, so it makes sense that that would be where that enzyme is most active. For sucrase, which goes in the small intestine, it obviously works on sucrose. We've already dealt with this idea of sucrase and sucrose forming their enzyme substrate complex, and then enzyme product complex, and then free glucose and fructose, and ready to do its sucrase work again. This happens at a pH that has an optimum of 6.2. Amylase in the pancreas acts on amylose, the starch, animal starch there, and that's between 6.7 and 7.0. Urease in the liver, which acts on urea, is about perfect neutrality of 7.0. And then we look and see we have some enzymes that work well above that typical optimum pH of 7.4. We've got our trypsin in the small intestine, which also acts on peptide bonds, the ones that the pepsin in the stomach didn't effectively break. You've got another chance here in the small intestine with trypsin working ideally at around 7.7 to 8.0 pH value. Lipases from the pancreas work on those lipid ester bonds, and that's ideally around pH 8.0. And then finally arginase in the liver, which will act on the substrate arginine, the amino acid there, has an optimum pH of well above 7.4 at 9.7. Another factor affecting enzyme function, of course, is enzyme concentration. So an increase in enzyme concentration will increase the rate of reaction if we're talking about constant substrate concentration, because more enzymes available to bind more substrate to that enzyme. So we see here an example where we start at 0 reaction rate for 0 enzyme concentration, and assuming we've got lots of substrate around and not so much enzyme, well, there's a lot of substrate waiting in that scenario. So if we can increase enzyme concentration, we can increase the reaction rate because we've got more active sites available, and we can have more enzyme conversion of that substrate into product. Now, if instead of looking at enzyme concentration increases, we look at substrate concentration increases, we don't see the same behavior. Typically, we're expecting lots of substrate to be around for the amount of enzyme that's there. That's why in the previous slide, if we're adding enzyme, there's likely more substrate to bind on those additional enzyme active sites. However, if we increase the substrate concentration, initially, we will see an increase in enzyme activity, assuming that there is enough enzyme to take on more substrate. However, if we continue to add substrate without adding any more enzyme, we're going to saturate all those active sites on the enzyme. So we're not going to be able to effectively increase the activity, the reaction rate, if we've already saturated the active sites. So once we've got so much substrate there that the enzymes can't turn over fast enough to have a new available active site, then we've reached that maximum activity that you see up at the top, because all the enzyme is combined with substrate, and just adding more substrate doesn't do anything. If we added enzyme, sure, we'd see an increase in rate, but adding more substrate when the enzymes that are available are all maxed out, we're not going to see any change in the reaction rate because we have all of our active sites saturated at that point. All right, so in keeping with our typical way of ending our lectures, we'll end here with a learning check. In this learning check, you're told that sucrase has an optimum temperature of 37 degrees Celsius and an optimum pH of 6.2. Determine the effect of the following on its rate of reaction. So we're given A, B, and C, and for each of those changes, go ahead and indicate whether you'd expect no change in the rate of reaction, 2, an increase in the rate of reaction, or 3, a decrease in reaction, and go ahead and put a 1, 2, or 3 for A, B, and C, and pause the video if you need a moment, and start us back up when you're ready to check your work. Good luck. Okay, so hopefully these are what you arrived at as well. So for A, increasing the concentration of sucrase, so we're increasing the concentration of the enzyme itself, right? Not the sucrose. Be careful. That makes a big difference because we talked about saturation behavior with the substrate and all of that. Here we're increasing the concentration of the enzyme, and therefore we would always expect 2, an increase in the rate of reaction. For B, changing the pH to 4, well, if the optimum pH is 6.2, then changing that pH to a different value, in this case much lower than our optimum pH, we would expect 3, a decrease in the rate of reaction for the reaction it catalyzes. And finally, for C, running the reaction at 70 degrees Celsius, likewise, since it's a body enzyme that has an optimum temperature of 37 degrees Celsius, it sounds great to increase the temperature to increase the rate, but of course, increasing the temperature to that level would denature the protein, the sucrase would no longer be active, and the reaction rate would markedly decrease, 3 again. So hopefully those are what you had for your answer choices as well. If not, please do reach out to me. We'll try to address any issues before moving on, but if everything's good, then we'll meet again for the next lecture in Chapter 20.